Goes off. Hi, welcome everyone to the stream. Today I am joined by someone from the Rasa research team, actually, Vova. Do you want to introduce yourself a little bit?
Hello, my name is Vladimir or Vova. I'm a senior machine learning researcher at Rasa, and well, that's pretty much it. Maybe a bit more introduction. So actually I'm not a machine learning person by education. I'm a physicist, but various practical and other reasons I started to do machine learning. So that's how I end up. There is. I don't know what else, Rachel. Should I?
um, Maybe where you're based. You're in the Berlin office,
Oh yeah,
right?
I'm in Berlin office. Yes, sorry. Yeah, sorry about that. Yeah, I'm based in Berlin. I'm now talking from Berlin from a lockdown. Yeah, I'm in Berlin office, but not from the office. From Berlin city, right? Currently.
The place where the office exists, but people don't go to right now.
Yes, the place for that exists, but for the reasons of global pandemic, it is not recommended to go there.
All right, so we're going to be reading, both of us for the first time, this paper. So for those of you who aren't aware, EMNLP, which is a big ACL conference, starts next week. They just released the papers. And one of the workshops is the workshop on negative results. So people sharing work where they tried something and it didn't work. And this paper sort of jumped out to me. And it is looking at bringing together different tasks and task-driven dialogue, so the sort of thing that you would use Rasa for, using generative transformer models. So looking at the authors, I don't actually know what generative transformer model they're going to be using, because there's somebody from OpenAI, which are the research group that came up with the GPT star models, Google Brain, which is where Bert is from, and then Mila, which is McGill's thrown a lot of money at machine learning research and building up sort of a research center there. So, question mark. So I'll start by reading the abstract, and then we can just sort of chat about it, and then start going through the paper. And the link for the paper is in the YouTube link. And Faiza and Ali say hi. Oh, welcome to the stream. All right. Task-oriented dialogue systems help users accomplish tasks such as booking a movie ticket and ordering food via conversation. It's like things you'd use Java for. Generative models parameterized by a deep neural network are widely used for next-turn response generation in such systems. Widely used? They are used.
Well, in research it is, right? So it's basically
That's true.
One of the main directions of the dialogue research is to try to generate the response. Not in Rasa, but in research.
Yeah, I would agree that it's a research topic, but like for commercial applications, I don't know that this is the default by any means. It is natural for users of the system to want to accomplish multiple tasks within the same conversation, but the ability of generative models to compose multiple tasks is not well studied. So like, I want to order a pizza for today and, I don't know, a calzone for tomorrow. So two different things that I want to do. In this work, we begin by studying the effect of training human-human task-oriented dialogues towards improving the ability to compose multiple tasks on transformer generative models. So using like human dialogue sets to do it automatically. To that end, we propose two solutions. One, creating synthetic multiple task dialogue data for training from human-human single task dialogue. And two, forcing the encoder representation to be invariant to single and multiple task dialogues using an auxiliary loss. So making fake data based on sort of this, I don't know, seed data of the human-human data. I'm assuming they'll talk about it, which I can't say as I, in general, would recommend. And then forcing the encoder representation to be invariant to single and multiple task dialogues using an auxiliary loss. So encoder, it's taking in the text, it's producing some sort of numerical representation of it. That representation shouldn't change between single and multiple tasks, I think is what they're saying. And they're doing that by introducing a new loss function. Is that what you're getting from that, Fova?
I'm honestly very confused by this phrasing, starting from human. So they say that they want of training human task-oriented dialogues, and then they say creating a synthetic multiple task for training from human. So if it is synthetic, then it's not human. If it is human, then it's not synthetic. Like at least maybe they give some kind of combination. I don't know. Maybe it will be clear from the paper, but from the abstract, I don't understand what is the training data look like. And therefore, the less is even more, like, first of all, so yeah, how do we, so the main question, and it probably comes from working right now on dialog manager, machine learning algorithms in general, is like, okay, transformer is beautiful, but over what? How does interplay between textual sequence and dialogue sequence comes in their model? That's also not. This is
I guess we'll see what they say.
I hope, but like, because from abstract, I'm a bit lost.
I would agree. And then they say, once they've done these two things that they try doing, the results from our experiment highlight the difficulty of even the sophisticated variant of transformer model in learning to compose multiple tasks from single task dialogues. So they're saying we had a hard time, which makes sense because this workshop is all about like, we tried and it didn't work.
I also would like to point out what you basically said at the beginning, right? Transformer is just an architecture. Not a concrete model, and here in this abstract they speak as if they kind of use the concrete model. So that's another thing that looks suspicious to me.
Yeah, I think they'll hopefully they'll talk a little bit more in depth about what model they're using. Do you want to read the introduction?
Sure. Like the whole thing. Okay, recent years have seen a tremendous surge in the application of deep learning methods for dialogue in general, and task-oriented dialogue specifically. Task-oriented dialogue systems help users accomplish tasks such as booking a movie ticket and ordering food via conversation. Generative models are a popular choice for next-turn response generation in such systems. These models are typically learned using large amounts of dialogue data for every task. And then obviously Budanovsky et al. Is the link to the famous multiple dataset. It is natural for users of the task-oriented dialogue system to want to accomplish multiple tasks within the same conversation, e.g. booking a movie ticket and ordering a taxi to the movie theater within the same conversation. The brute force solution would require collecting dialogue data for every task combination, which might be practically infeasible given the combinatorially many possibilities. Well, that's hard to argue.
Yeah. Okay, so what they're saying is you got multiple things you want to do. If you want to represent this using, text generation, you need to have examples of people doing those multiple things. And this almost seems like worse than building rule-based systems that handle every single path and every single combination of paths as a set of rules, right? Because you need those same paths, but you have to get humans to do them naturally, and then train a model that'll do it. I don't know, this seems awful. Not that I think like necessarily the core problem is bad, but like the approach of having a lot of dialogue data that covers all these paths seems, I don't know.
But that's what they mean,
Rough.
right? So that's exactly what they mean, that we cannot have all possible paths.
So what do we do?
While the ability of generative dialogue models to compose multiple tasks has not yet been studied in the literature, not sure about that, there has been some investigation on the compositionality skills of neural networks. Lake and Baroni propose a suite of tasks to evaluate the method's compositionality skills and find that deep neural networks generalize to unseen compositions only in a limited way. Analyze Code 2 et al. Analyze whether the language emerged when multiple generative models interact with each other is compositional and conclude that compositionality arises only with strong regularization. I guess we need to write these papers linked in order to assess the, let's say, whether this
claim is correct.
Exactly, yeah.
Yeah, and this, there was a paper, I don't remember the citation off the top of my head, but it was looking at trying to create training data for dialogue systems by having, agents, not people, but like systems interact with each other to produce data. And they found, and I think that sort of like anecdotally, this seems to be the case for a lot of folks in industry as well, that having, systems talking to each other, those systems tend to get like degenerate results, like results that you wouldn't want to use or that don't reflect the way that people use language very good. Yeah, and that's been my sort of general impression of the literature, that it's perhaps possible to do things where you have multiple generative models and using that as a way to produce data and systems, but that it is, if it is possible, very tricky.
I guess that's what I mean by strong regularization. I'm not sure. Regularization is nowadays used in
means a lot of different things.
Yeah.
And at that point, like, if you're, babysitting these models with like, a lot of additional infrastructure, maybe at that point generative models are not the best choice. I don't know.
Exactly.
Just from a simplicity standpoint.
Yeah.
And I can take the next section. Motivated by the practical infeasibility of collecting data from combinatorially many task compositions. So you could get out of this with more training data, but because you have, if you have 2 tasks and you want to combine them, you'd need 4 sets of examples. If you had 3 tasks, you need 9. So like as you start to combine things, you get, many, many more combinations. It's just what they're saying there. We focus on task level compositionality of text response generation models. We begin by studying the effect of training data size of human-human multiple task dialogues on the performance of, just the vanilla transformer generative models. Okay, so they're seeing, does adding more data make the output better? Is what they're getting to there. So I'm guessing they're treating this as just like a sequence to sequence problem, where the input sequence is probably the whole history of the dialogue and the output sequence is probably the next turn. Hopefully they talk about this more. Next, we explore 2 solutions to improve task level compositionality, so sticking tasks together. First, we propose a data augmentation approach, bunch of augmentation references, where we create synthetic multiple task dialogues for training from human-human single task dialogue. Okay.
That's,
so I'm guessing that
human into play go.
Yeah, like cutting and pasting multiple dialogues. Like, I bought a movie ticket, I ordered a taxi, it was 2 separate interactions. We're going to pretend it was 1 interaction, just like stick them on, is what I get from this. We add a portion of 1 dialogue, as a prefix to another to simulate multiple task dialogues during training. Okay, so this is what they meant by the synthetic human-human data. Would that work? Or would you get weird results? Based on the workshop that this paper is in, I'm guessing you get weird results.
Yeah, I just wanted to say that. Yeah, you mentioned the meaning that it's negative results workshop.
Mila says, will there be an office hour where we can ask questions about code? Yep, the office hours are on Wednesdays at this time slot, so 9 a.m. Pacific. We had one yesterday, and the next one will be next Wednesday. And Faiza says, excited for tomorrow, and then questions about extracting names. I think probably Spacey has a name module, but I would ask that on the forum, would probably be a better place to get an answer to that. That's actually helpful. As a second solution, we draw inspiration from the domain adaptation literature and encourage the model to learn domain invariant representations with an auxiliary lost to learn representations that are invariant to single and multiple task dialogues. Wait, so are they treating single task and multiple task as separate domains? So usually, at least when I've heard domain used, it means like banking versus, e-commerce versus, food ordering. So the separate, I think a lay term would be like topics. This seems more task.
In here, they use the words domain and tasks interchangeably.
Yeah. Yeah, I would say, at least the way I would use the terms, task is more specific. So a task is like a specific thing I want to do, and a domain is sort of the general topic that task exists in.
Yeah, I would also do that, but I guess in these data sets, and for example in multiverse, look at it, and usually they kind of similar because, for example, if you want to book a hotel, which is a task, but you're creating the domain of hotels, and if you want to order a restaurant, book a restaurant, then you can argue like it's a different task, and you can kind of create a special domain for this task as well. Then you kind of have different domains as well.
Yeah, okay, I can see that. So it almost feels like sort of an artifact of the fact that multi-WAS is so popular as a research data set, and then the terminology used in that data set sort of like trickles out through the research community.
But I think it's everywhere. I think it comes more from the fact that all of these data sets, even if they're human, they're still artificial, right? To kind of set up a task and then set up a domain for this task. Rarely the domain is bigger than the task, because not that they take a real pizza ordering system and get the conversations from there.
Yeah, I think the so last week we read the Hint 3 paper. I don't know if you read that. It was also from EMNLP, or possibly one of the workshops. And they had like actual data sets that were collected from actual people using systems. So there was one for like ordering mattresses, I want to say, and one from like people who needed support for an online mobile game, and then the third one that I have completely blanked on. And then within each of those domains, like those are dealing with different topics, there were multiple tasks. So that might be a good data set to use if you were interested in like actual data.
Yeah, maybe
that's a little rude.
I didn't paper, but maybe.
All right. Oh, here it is, multi-WAS. Do you want to get the next couple sections?
Our favorite. Conduct our experiments on the multi-WAS dataset. The citation of the multi-WAS paper. The dataset contains both single and multiple task dialogues for training and evaluation. Multi-WAS, the tasks in multiple task dialogues are only the combinations of tasks in single task dialogues. This allows the dataset to be an appropriate benchmark for our experiments. Okay. To summarize, our key findings are: study task-level compositionality of text response generation models and find that they are heavily reliant on multiple task conversations at train time to do well on such conversations at test time. We explored two novel unsupervised solutions to improve task-level compositionality, creating synthetic multiple task dialogue data from human-human single task dialogue, and second, forcing the encoder representation to be invariant to single and multiple task dialogues using auxiliary loss. I guess that's what they meant in abstract that we didn't understand. Now it's a bit more clear.
Yeah.
Highlighting the difficulty of composing tasks in generative dialogues with experiments on the multi-voice dataset, where both the methods combined result only in 8.5% blue score improvement when zero-shot evaluated on multiple task dialogues.
Oh, improvement. I was like 8.5% blue. Jiminy cricket.
Blue. Wonderful.
Oh. Do you want to talk a little bit about multi-was? Because when it's come up, you sort of like made a face.
Yeah, well, multi-was. I'm a bit biased about multi-was. We released a paper where we say that according to our experiments, the multi-was is not really history dependent, right? Like most of the utterances can be predicted from. If they can be predicted, they can be predicted directly from the previous user input. Is the first problem. The second problem is that multi-was is unlearnable by deterministic machine learning system, because in identical cases there are different answers. Like Wizard, what's supposed to be a bot, right, behaves differently. Because it's just a human who typed whatever they wanted to type. But then you cannot use the deterministic, what is any neural network is after it is trained, it is deterministic system. It cannot predict different answers in this case. And more importantly, how do you evaluate this when a number of utterances could be correct from the point of the data set? Yeah, therefore, in general, benchmarking on multi-was to me doesn't make sense. Like, so any numbers that are accepted there is like how well your model can, like, it's even very hard to put into the wellness of the model, because the answer is stochastic and the model is deterministic.
So it almost feels a little bit like some of the problems with evaluating machine translation. Not machine learning, Jiminy cricket. Machine translation when there's multiple correct answers, except this is supposed to be generated by a system that always gives you the same answer, and in the data set, because people are pretending to be systems, it doesn't.
So it's like, so maybe in machine translation you want some generative, I don't know yet, I'm not sure there. But here it's, yeah, here it's, but the evaluation kind of problem is the same. How do you evaluate the answer that can be correct? And blue doesn't always represent the paraphrase, right? So most of the time, of course, these answers are paraphrases of each other, but blue score doesn't really captures paraphrasing.
Yeah, and it's just as a plug, blue score is supposed to be a corpus level measure. So please don't use it on the utterance level. Your results will be meaningless. Sorry, blue is one of my...
half of the papers of the whole NLP, probably.
If you get very specific comments like that about blue, I'm not saying that I'm the reviewer, but it's a reviewer who agrees with me.
No, I totally agree with you. I totally agree. I'm just saying that that's what majority of the papers rely on, is like how much improvement on blue.
Yep. Anyway, let's read about their method. So let D1 through DM be the dialogues in the training set, and every dialogue DM is made up of utterance 1 and then answer 1. I'm assuming that's what curly U and curly A mean. That might be an alpha. I don't know. I can't tell Latin numbers apart. For all things in the set of 1 through M, where M is the number of turns of each user and assistant. So a dialogue is made up of an utterance and an answer, and every utterance gets an answer for, you know, the number of turns that there are in the dialogue. Further, each user and assistant turn consists of a sequence of word tokens. The individual dialogue could be either single task or multitask, depending on the number of tasks being accomplished in the dialogue. A sequence of word tokens is a pretty strong assumption about what people are going to put in a system, but this is, you know, very clean data, so we'll assume that they're right about that. the response gener
Just one comment maybe. I love when people add mathematical notations where it completely doesn't make sense. Like you don't need these math notations to describe a dialogue. Just makes it much more complicated, but makes the paper looks more diverse.
well, makes the perhaps it makes your viewers glaze over a little bit. They're like, oh yeah, math.
Exactly, yeah. Well, it's not. It's just describing the dialogue. Yeah, sorry.
Oh, no worries. Simon says, could you give us a quick intuition why blue makes sense to be used on a corpus but not on utterances? And I think the quickest way to do that is to send you a blog post I write. I'm gonna look that up really quick. Because it goes into it in a little bit more depth. But basically, it's not intended to be a like something that you would compose over multiple utterances. All right. The response generation model is trained to generate each turn of the assistant response given the conversation history. Hey, called it. So the input token is everything that's been said, and then the output is one turn of assistant utterance. The user utterance is like appended back into the system, answer, bring it out, append the user utterance back into the system, get the utterance out, and so on. The generative model learns a probability, the probability of a distribution given by the probability of a specific answer given the entire history of the conversation, including the last user utterance. It's just what all this means. We drop the symbol M to denote that a particular training example for simplicity. The assistant turn AI consists of a sequence of word tokens. AI is made up of a sequence of word tokens, where each of these is a word token. The response generation model factorizes the joint distribution left to right given by, all right, why does this one not have an equation number and this one do? All right, so the probability of AI given a xi, where xi is the conversation history that comes previously. We're looking over words in the vocabulary.
Yep.
And then picking the most probable next word recursively.
I mean, it's just whatever they described above. Just pick the calculate the probability of the next words given all previous generated words and all the history of the dialogues represented by X.
Yeah, and then
it's basically you type all the possible models by this equation.
And they do this using. Actually, do you want to take the next little bit? I don't want to read another equation.
Yeah. We use a transform, so this is just a meaningless description of how statistical inference is made. It doesn't describe any details, or it's not this equation without a number to the model. It's introduced here for, as I said, as a mathematical equation where it is not needed. We use a transformer, sequence-to-sequence model to parameterize the above distribution. Okay, so now basically that's what they use. Given a training set of dialogues, the parameters of the transformer model are learned to optimize the conditional language modeling objective given by classical objective that the log probability basically should be maximized. And it's this above probability where theta is the, yes, exactly, where theta refers to the parameters of the transformer model. Yeah. It's basically rephrase the equation above, summed over all dialogues, all examples, and dialogue steps, I guess.
A turn, assistant turn.
Yeah, exactly. Yeah, so sum of all turns on, and then that's also very standard. There's nothing. It's basically any model can be described with this equation. So yes, let's go forward.
All right, data augmentation. The first solution we explore for task compositionality generates synthetic multiple task dialogues for training from human-human single task dialogues. 1. Code repository. Oh, that's nice. I think that this is kind of inherently a flawed way of approaching this because, so if we, starting right now, treat the rest of this conversation as a separate turn, it's still going to rely on the contextual knowledge that you and I share based on the previous parts of the conversation. So in actual human interaction between humans, you can't pretend that there are joints in the conversation where all of the previous context is ignored. Even if that context is only like stylistic, level of formality, in a multilingual setting, what language you're using. Even if you change topic dramatically, there's still going to be, a dependency. They're not independent. There's no way to like break a conversation down between two people that is continuing, or a human and assistant, into completely independent steps. And they're sort of assuming that that is the case by taking these independent steps and concatenating them like this. This is like, from a linguistic standpoint, this is funky. This is not a good representation of the way that humans work. But also, data augmentation is almost always a little bit funky. So like for image augmentation, you'll flip and rotate and do things to an image just to make it appear in more different ways. So that's, as a linguist, I'm like, As an engineer, I'm like, I kind of get it. But also, given the workshop, I don't think this works.
But I don't think they kind of claim that it is a good solution, right? So that's kind of the first solution that comes to mind. So I think it's fair that they say, well, this is the first solution that comes to mind. Let's. We don't expect that it would solve the problem, but at least let's see, what does it bring.
Here we sample 2 dialogues from the training set and add a portion of one dialogue as a prefix to another. Well, this procedure may not, oh, here we go, create dialogues of the quality equivalent to human-human multiple task dialogue. It is an unsupervised, i.e. we didn't have to label any training data, way to create approximate multiple task dialogues that the model could theoretically benefit from. So saying like, hey, we know this isn't ideal, maybe it'll work, let's see. I can get the next section as well. Concretely, we randomly sample 2 single task dialogues, DI, DJ, from the training set and create a noisy multiple task dialogue by adding a fraction of the DJ as a prefix to DI. Oh. So part of one task to a second task. So we have a whole second task and then just like a random little snippet from another task added to it. Oh, this feels even more funky. The fraction of the dialogue taken from dialogue J is given by the hyperparameter augment fraction. Okay, so they try adjusting how much of a snippet they use. The number of times dialogue DI is augmented by a randomly sampled dialogue is given by the hyperparameter augment fold. Okay, so they've got like a bunch of different stuff that they put in front of it, and they're tuning that. Yeah. You want to take the next section?
Yeah. We consider 2 strategies for sampling the dialogue DA. Random augment, that's the name of something, I don't know, algorithm. The dialogue is uniformly randomly sampled from the remainder of the training set. A potential issue with the random strategy is that it might create spurious task combinations. The model might fit this noise. Created by this spurious task combination phenomenon, we consider another sampling strategy, targeted augment, where we create synthetic multiple task dialogues only for task combinations that exist in the development set. Here, DJ is sampled from a set of dialogues whose task is compatible with the task of dialogue DI. The Prasanna model is now trained on the augmented training set using the objective function given in question 1. The effect of the sampling strategy and the hyperparameters on the model performance is discussed in the experiment section, where they create a synthetic multiple task dialogues only for task combinations that exist in the development set. It's a bit of a...
So they're trying to match the distribution of things that they're going to see in the test data set, basically, with the data that they train their model with, which
is reasonable if you have a development set. The question is, it's kind of
yeah.
a little bit, leaking of the information from the test sets, so to say, because if you develop a bot that you don't know in which combinations your users will talk to it, then how do
you're not going to have access to that sort of guide of what tasks to put together. Yeah, so this might be, I mean, if you wanted to apply this sort of approach with a Rasa assistant, once you have your assistant in front of users and they're starting to use it and you're like, oh, people are doing these types of tasks together, maybe you could go back and, recombine people doing other tasks from other dialogues. But I would say maybe don't. Again, just based on what we've got so far, I think you'd probably be better off just adding the multitask turns or the multitask like interactions that you see as stories to your assistant and then retraining. Also, it's simpler, just easier. Okay, who read the last section?
I read the last.
Okay, I'll read this one. I'm doing great. I got a little coffee left. We propose domain invariant transformer model, figure 1, to maintain a domain invariant representation of the encoder by training the encoder representation for an auxiliary task. Here, the auxiliary task for the network is simply to predict the label L hat, I think that's an L, denoting the type of task, single or multitask, in the encoded conversational history. Okay, so they have to predict whether the type of task, coded conversation. So it's looking at the history and being like, this is single task, this is double task. So I think well, they'll talk about it more, but if that's the task and a priori whether a conversation is single task or double task and you're providing that to the system, that feels very funky to use at inference time, because if someone's just coming in and using my system and they're like, hi, I don't necessarily want to try and predict how many things they want to do. Like, I don't know how you do that, right? I don't know how that would work if you don't have this huge label training set. No, but presumably they'll talk about it more.
In their case, they have so which are the generated multitask and which are the original. They kind of have this label for free.
So I'm saying that they definitely have this label while they're training the model. I guess we'll see how much it helps.
Yeah, let's continue, because we're guessing what they're gonna do. Let's just.
Let's start. The L hat. The model takes as an input sequence byte query encoded tokens that are represented at the encoder hitting state as a set of attention weights from a multi-head, multiple layer attention mechanism of a transformer. So it's just taking in the weights from the transformer for a specific sequence of tokens. And all of this is like transformer specific stuff. You should watch Vincent's algorithm whiteboard videos if you want to learn more. He's got some really good explanations. David says, with the limited knowledge I possess, this seems very advanced and goes right over my head. I would say this paper's pretty in the weeds. But yeah, if you have any questions or there's a term that you're like, I don't know what that means. That's what we're here for, right? Is to learn together. The conditional language model, equation 1, is learnt by a transformer decoder on top that intends over the encoder states. So basically, this is just like a basic transformer architecture. If you're not familiar with them, just know that that is what they're doing. The discriminator task network, so this is the auxiliary task, is trained over average pooling of the encoder summary over the intention heads as shown in equation 2. Okay, so we have an encoder, decoder. After the encoder, we have a secondary task, which is detecting whether it's multiple task or single task. Equation 1.
Yeah, let's read further. I guess they will present it. Equation 1 is this equation with the condition.
Just like what a language model is. Enrique says, great videos from Vincent. Yeah. All right. The discriminator task network is trained. Average pooling shown in equation 2. So E is I is turns, right?
Yeah.
I'm pretty sure this is for every argument.
And J is the token over the tokens. Basically, it's average transform output in simple terms. You get for each token, you get a transform output, you average it out, and that's what you feed into whatever is called discriminator task network.
Is this?
Yeah, I guess.
Have we gotten to here yet?
Presented by this.
Okay, so they've got. Yeah, so they have the words to the encoder, and then from those representations, you get this guess about multitask, single task that you are trying to get right as often as possible. And then also you get from the decoder your actual output turn that you're going to tell the person who's using the system. Yeah, so it's a little bit similar to the structure in the transformer where you have a little like loop around each one of your feed forward layers. It's similar to a gate, but it's not called a gate.
Connection?
Yeah.
No, but I think
one.
it's independent. No, I think it's independent. So basically, I mean, I guess it's better to read it through, but from the look of it, it's literally simple, like an exact transformer with all the residual connection inside these big rectangulars, and you just take the output of transformer goes to decoder token by token, but you also can take this separately output, average it out, and put it in a different network. I assume that this different network is a simple multi-layer perceptron or something.
That feels right. I guess we should see what they say. So we're just averaging. Is actually, you can take the next section. I've been talking for a bit.
Average pooled encoder summary is passed as input to a two-layer feed-forward discriminator. Yes, multi-layer perceptron. The discriminator network has a dropout layer in between the two fully connected layers, F1 and F2, of pointless equations, y equal F2 of F1 of E. The binary cross-entropy loss L for the predicted label y and input context I is computed as in equation 4. This is a standard cross-entropy loss for the binary classification task, also pointless equation. And yeah, the domain the main line transform model optimize a convex combination of the two losses as shown in equation 5. Okay, this is the first interesting equation. You said I don't see comments unfortunately, but there was someone who said that this paper is too complicated. It looks complicated because of all these equations, but so far I guess we can recap what they did, and it's actually relatively straightforward. So what was the original problem is that you usually have some human-to-human dialogues in one domain, like the number of dialogues for booking a restaurant, the number of dialogues for booking a hotel, and then maybe many more tasks. Again, in this particular, I guess they interchange task and domains, so I might mention that as well. But if you want to have a dialogue to train a system that could be able, in the middle of booking a restaurant, also book a hotel, one will need an additional, mixed dialogues. And this, as you, Rachel, pointed out, that you need actual real dialogues to represent the real users, but let's assume we cannot afford it. So the question is, what kind of artificial things, what strategies can we come up with without collecting more specific data? Because if you have a lot of tasks, then combining all of them, it's like a huge data set. The first idea that they come up with that we discussed already is just simply concatenating in a random or mixing up random parts of dialogue. As Rachel mentioned, from the linguistic point of view, it doesn't feel good. However, again, given that like, we don't have any better, let's try this one. And then they take the very standard transformer architecture. They take the dialogue in terms of all the, like, imagine that you have a dialogue, right? Then you start writing your texts that appear in your dialogue vertically from left to right. And you create a huge novel with sentences one after another. And this novel, this one-line sequence containing many sentences, is basically an input, your transformer. Now, based on this input, they try to come up with the answer, with like a short answer, which will be a next turn. And that's basically this called language model loss. And they say that they want, for some reason, one another also to add to tell the model to, like, try to teach the model to distinguish between if it was single task or multitask. And therefore they kind of keep out the middle of the encoding, kind of you can imagine this as a whole, this like dialogue turn embedding this average output of transformer to a different smaller neural network with a binary classifier on top that will say tell us whether it is single task or multitask. And then they combine these two losses together with the weight parameter alpha, which I think we did actually read it. So yeah, exactly. So this L train, as I said, it's a combination of two losses. One is alpha L disc, I guess it's discriminative model, and plus minus alpha L language model. And I guess they will tune the alpha. The language model loss makes sure that the model learns to generate the next utterance, while the discriminator loss makes sure the model is aware of the nature of the task. To understand the effect of the auxiliary loss, we experiment with different values of alpha in appendix. Yeah, alpha is a hyperparameter. It's a classical multitask problem. You don't know, so the losses have different scales, so to say, and you want to scale them correctly so that they're trained well. So in principle, like, it's the idea, it seems to me, it is not that complicated as they present it with all these equations.
Yeah, I think that's a pretty good summary of what they're working with. Also, I've been like, I just realized my mouse doesn't show up on the on the screen, and I've been like helpfully like circling the parts of the diagram that were relevant with my mouse, but I'll fix that in the future. All right, so experiments. This is usually part of the paper that goes the fastest. We measure the importance of multitask dialogue on the overall performance of the transformer by training the model with varying amounts of multiple task dialogues and keeping the task distribution between multiple and single domain dialogues almost similar in the experiments. Almost similar. We keep increasing the number of multiple task dialogues while reducing the single task dialogues to keep the total number of dialogues consistent at 2,150. Sorry, 2,150. I thought that was like a.
Yeah. I also thought so.
That was like a list of two values. The model should be able to learn to generalize to multiple tasks, as the set of tasks are the same between the train and test sets. Nice work if you can get it. With only the nature in which the task is posed by the user is different. We use the tensor-to-tensor framework to run our experiments with tiny hyperparameter setting in the framework. So little 8x80 transformer. Oh, we have a question. Marco says, transformer is nice. Yeah. And Elon says, any model available for extracting entities related to specific domains, banking, retail, healthcare, similar to Duckling, instead of teaching the model with domain-specific data. Maybe. I don't know of any off the top of my head.
No idea. Sorry.
Okay, so this is just, they're talking about the mix of different training data that they're using. Oh, and here's a table. As shown in table 1, the quality of the model improves significantly as the number of multiple task dialogue increases. So one thing that is interesting to me is they talked about the number of dialogues, but what they don't talk about is the length of the dialogues. And I would assume that, a similar number of longer dialogues is probably because that's more training data, right? That's because the task is to generate turns. Your model's going to have more chance to generate more turns, so more time to, sort of bake, as it were. So I would want to see fixing the length of these interactions as well as the total number.
Absolutely. Because
Okay,
also,
so even
when they concatenate the dialogues, they also increase the length, right? So if they...
Yep. Yeah, so I would expect, just like a priori, using this, you could probably even get better results with a smaller number of multiple task dialogues, just because there's going to be more training data. All right, so total number of dialogues are kept fixed, which is good. That's one variable that you should fix. The overall validation blue scores also improve as the number of multiple task dialogues increase in the training set. Yeah, the results show that the models may do better at decomposing than composing in the domain of goal-oriented dialogues, or the model at best can only mimic surface-level token representation. Okay, so they're arguing that this finding is evidence that models may be better at decomposing, so breaking things apart, than composing, putting things together in the domain of goal-oriented dialogues. Okay, sorry, I'm just gonna look at this. So what we're seeing is, at the top, all single task, at the bottom, majority multiple tasks. So as we go down, we get more and more multiple task dialogues. As we go down, overall, the system performs better. And the multiple only dialogues perform better.
What is multiple only versus overall? I don't get.
So I think this is on just dialogue tasks where there are multiple tasks. Or sorry, dialogues where there are multiple tasks. So I'm guessing that multiple only is multitask only.
Okay, but then I have a question: how come if you only have single task in your training data, then multiple only is higher?
Yeah.
Is overall contain both single task and multiple only?
Yeah.
Because it's weird that, if you have only single, then multiple only is higher than overall. Which I would expect vice versa, right? So like,
yeah,
you don't have any multiple training data, then your multiple only is low, but overall is still because you test on the single data.
Yeah, I would agree. It is weird. And also there's a point here.
They become like they increase the number of multiple dialogues, but the overall grows faster, which means it performs better on single turns, which might be due to your reason that they simply increase the length, which they increase the training data.
Yeah, particularly because of the way that they're like composing things, having like the context is not as important. Let's see what they say about it. Better at decomposing than composing. So going from multi to single, then single to multi. Though training with more multitask dialogues can potentially improve the performance, it is not a scalable solution. We will test two of the off the shelf. Sorry, I thought I was going to say out of fold. It definitely did not. We test two of the off the shelf. Usually it's said off the shelf.
Out of the shelf techniques to I don't know.
The test. I think it's just like a little. It's an idiom that I'm not familiar with. Techniques to improve the task level compositionality in the following section. And just as an aside, if you're learning English, prepositions are the worst, and I'm very proud of you because they're just random in English, basically. Beginning with the chat. Hi, a lost algorithm. Frank says, but that would mean that they try to achieve something, whereas I as a user can switch between tasks on every turn I make in the extreme case. And in the end, I accomplish booking a hotel and ordering food. Yeah, so they're, the way that they're doing it is that they're sort of like, pasting things on the end rather than interleaving. And I don't know how. My gut instinct is, given the architecture that they're using, it might actually work if you just sort of like switch tasks every turns. Because transformers care less about the distance of dependencies in the dialogue than other models do. Yeah, no, it's a good point. All right, you want to take the next section?
Yeah, the experiment on transformer to evaluate the performance on handling zero-shot compositional tasks by training the base model only on single-task dialogues and with the proposed data augmentation. It's not zero-shot then. Wait, again, sorry. The experiment on transformer to evaluate the performance on handling zero-shot compositional tasks by training the baseline model only on single-task dialogues and with the proposed data augmentation techniques.
Okay, so not having any examples of human-human multitasking
Okay.
is what's making it zero-shot.
Okay.
Zero-shot means no training data.
Yeah, but it's not, yeah, okay. it's a matter of using the word. The results in table two show that the target augment, single task dogs, random augments. Wait, let me finish the reading. Technique show that the target augment technique increased the performance on multitask dialogues by 8.5% blue score, while the scores of the model slightly dropped in the performance of all dialogues.
Okay, so I think the targeted augment is where they're trying to match the distribution of tasks in the testing and training data. And the random augment is I'm just randomly taking another task and adding it to the top of the task that I'm trying to do now.
Wow, that's hardly surprising, right? They just kind of introduced a bit more knowledge about the training set by only augmenting the tasks that exist there. So it's like, would be surprised if it dropped.
So in a situation where you didn't have access to the testing data set, you wouldn't be able to use this targeted augmenting technique, even though it does look like, so blue is going up. And interestingly,
yeah, it's very confusing to me. Yeah, it's exactly
this is the opposite.
Numbers.
Okay, so this is just a
wait. In text below this data.
Oh, sorry.
Yeah, the reason for only a minor blue improvement could be due to the noise in generation process. Although the task distributions are matched, the token level distributions appear to be significantly different on top. Yeah, different between the single and multitasks. That's exactly what, Rachel, you were talking about. From a linguistic point of view, it's a different thing. The results suggest that the method may inject more noise in the token level distribution, thereby not improving the model performance significantly. Yeah. Or it can suggest that from linguistic point of view, simply concatenating phrases is not multitasking.
Yeah, so something that jumps out to me here is that if we're looking at the multitask utterances, this targeted augmentation helps. But targeted augmentation actually hurts overall performance as well. You can see that if you have the just sort of like the random augmentation, it does better than just the single task, but worse than the targeted augmentation. So if you have a mixed single and multiple tasking, and I think they're suggesting that that's due to just noise.
I would say it's just it's more of a point that by doing the random augmentation, you increase the length of dialogues, effectively increase the training data for a single task, and therefore the overall performance increases. While in targeted augmentation, you don't add as many single tasks, right? So you only hand-picked single tasks. Therefore, the overall performance doesn't increase this much. So I would argue that they created a method to help single task augmentation, but not really multitask.
Which is, I mean, that's interesting, right? That just like concatenating more turns does seem to, if you're using this particular method, it does seem to be a viable way to do data augmentation for dialogue, perhaps.
No, I think it's artifact of this property of multivoice that I was talking in the beginning, that your answers are highly random, like really non-consistent. Therefore, when you add more data, you kind of increase, maybe you include more variance, or maybe you make some answers more consistent than the others, then these answers be predicted more often, and then your blue scores increase slightly. But I wouldn't, like, to me, this means nothing. Like this changes is blue, it means that there is no difference between these three models. This is the only result that I would read from these numbers.
I think that's a very fair point. And these are also weensy little changes given the noise and the data. All right, domain invariant transformer. So this was their sort of like adding more data approach. Meh, sort of the results. And then this one is adding the objective of predicting whether something is multi or single turn. We compared the proposed architecture and the baseline transformer model to understand the effect of domain invariant encoder representation towards language generation in multitask dialogues. We observed from our experiments in Table 3 that domain invariant transformer or transformer models failed to generalize with few-shot multitask dialogues. Okay, so if you train it on a few examples, it doesn't generalize well. It might be overfitting, potentially. The data augmentation techniques, too, do not appear to contribute towards improving the performance. But domain invariant transformer models improve the performance to a blue score when training only on all of the training data, which was not the intended objective. Okay, so they're saying that this architecture that they propose, they only see an improvement when they're training on all of the training data. I don't know if you heard that like little like grumbly. That was my dog. He came in to see if I was available for playing, and I am not. Although that seems good, the model is still heavily reliant on human-human multiple domain dialogues, and zero-shot or few-shot generalization in compositional dialogues seem quite difficult to achieve. Okay, so 0.5 and 1 correspond to half and all of the multitask samples, respectively, during training. Synthetic refers to the target augmented dataset. All right, so what's going on in here? We've got a bunch of blue scores. And
I guess the first one is the original transformer model without any of their techniques trained on all real and all multivoice or something? All real data?
I'm guessing that this is sort of their baseline.
Yeah, wait, table 3, 0.5 and 1.0 correspond to half and all of multitask samples respectively during training. Yeah, I guess this means one means that there is all multitask samples from the original data set, multivoice, and that's the kind of, that's baseline when all multitask is here.
So I think what they're doing here is they're saying, hey, when we add synthetic data, because these both have synthetic data, and then we reduce the amount of the original multi-training data, what happens? And it looks like adding synthetic data just like throws a wrench in the works.
But look, the third line in here, that there is one, it means that there is all training data plus synthetic data, and the blue is lower. So the synthetic augmentation destroys the performance of the model.
Yeah, which I think this is honestly very helpful, right? As a result, because I think it's good evidence that even when you start to add, this additional task of detecting whether or not something is multitask, which if you're using all the training data, looks like it might help. So this little architecture change, adding synthetic data makes it worse. So I think that this is good evidence that if you're trying to, create additional training data to, have your system perform better, specifically with people doing multiple things, don't. It's not going to help.
But look, another interesting something that they didn't mention is that the discriminator transformer model, in the presence of the synthetic data, performs worse than a normal transformer model.
Oh, that's true, yeah. So these numbers are lower.
Things worse. So I would argue the discriminator also questionable, because then why would it make, I understand why synthetic data makes it worse, okay, but why would the discriminator make it?
Yeah, I wonder if it might be in part because this discriminator is learning whether or not it's synthetic data, right? Because it's determining whether it's single or multi-turn, and a portion of the multi-turn ones are going to be synthetic. So but I don't think any of the single turn ones are synthetic. So my guess is that it might be sort of muddying up the results for like multi-turn or multitask. Sorry, these are all multi-turn, multitask things in general. Interesting. So yeah, we need human data.
Yeah, the poor performance.
The poor performance of the data augmentation techniques can be due to the overwhelming noise and token distribution of input contexts, which skews the language model that the model learns. So the data augmentation is introducing noise. It's probably not a good representation of what the data that humans would produce in the wild doing the same thing would look like. So it's, in this case, it's not helping, which I think is, I probably would have phrased this, personally, I probably would have discussed these experimental results in a little bit of a different way. But yeah, I think that's a helpful finding, right? If you're like, should I do this? Probably not. I wouldn't recommend it. All right, do you want to take the conclusion?
Yeah, we studied the problem of composing multiple dialogue tasks to predict next utterance in a single multiple task dialogue. We found that even powerful transformer models do not normally compose multiple tasks, and the performance is severely relied on multiple task dialogues. In this paper, we explored two solutions that only further showed the difficulty of composing multiple dialogue tasks. The challenge in generalizing to zero-shot composition is observed in the experiments. Hints the possibility of transformer model potentially mimicking only the surface level tokens without understanding the underlying task. Token overlap distribution in appendix.
Yeah, I think that it is not controversial to say that there is no sort of model of conversation in just generative transformer models. Yeah, I can peek at the really quickly. I was looking for like the token distribution. Okay, so here's an example of how they're composing things. Okay, so they're taking sort of like the end of a task, basically, where the assistant's like, hey, what else do you want to do? And then adding this bit where the user's like, oh, I'd like to, do something else. And instead of that being the first thing they do, it's a different thing.
It's not the end, they're part of the task. If you see on the right, the red one is not finished, so it's even worse.
Oh, yeah.
Yeah.
No, I see. So they're talking about, is there anything you need to know about this hotel? And then there's a pretty abrupt transition to talking about trains. Yeah.
No wonder it makes it worse.
I think it's interesting because it's not, like I mentioned, this sort of composing things does give you more training examples, right? And in general, transformers do better with more data, and deep learning in general do better with more data. And I think this is an interesting case of an example where more data does not help. And especially coming from like a a computer vision data augmentation background where like you can just, flip an image and it works perfectly fine, that you can't do the same sort of like cut and paste as well and get good results with dialogue data. Yeah.
Well, computer also didn't try generation, as far as I know, right? At least this augmentation is used for classification tasks.
Mm-hmm.
And any classification task is simpler than generative. So yeah, well, I don't know. I kind of, I guess the first problem is not even whether this helps or not, but how to measure the help, right? So we know that the blue score is a poor indicator of whether it helps or not. And the multi-voice is also the poor indicator of tasks, So kind of, to me, this paper didn't add any sort of knowledge whatsoever, right? The problems with, I think you perfectly summarized the problems of the augmentation from linguistic point of view. You know them kind of without this paper. And they didn't, I mean, if they try to analyze the mistakes that this model trained on synthetic data versus model trained on real, which was also not real, but still human data, we could get some insight what sort of mistakes it does, what this synthetic nature leads to, but simply
more of an error analysis.
Yeah, something like that, right? Comparing blue score for me doesn't give any doesn't rule out this method of augmentation, even though I agree with you that it's not a perfect method, but still.
That said, as I think we mentioned, using blue scores and using multi-WAS is super common and standard. So I definitely get why researchers do it. And it definitely, I mean, like, for better or worse, makes it easier to get your paper published. And I think it was a paper we read a while ago where like they were doing analysis on a bunch of data sets and there was like multi-WAS tacked on at the end, and I was like, oh, a reviewer probably asked for this. And it was probably not necessarily because it was the best fit, but because it's a thing that everyone does, if you know what I mean. Yeah. And Lost Ogden says, I don't know if this generalizes to non-synthetic data. The code to mix dialogues looks odd. Yeah, it is a little bit funky, but I don't know if there's any way that you could do the mixing that wouldn't be funky, right? Because it's artificial. So, yeah, overall, I'd say interesting. I think a good fit for the workshop it's in, which is the negative results workshop. Yeah. And you have any last comments, Vova?
No, I mean, I think we covered this already. I think there could be more interesting things. To me, this is not finished. To me, this.
Yeah, no, I could definitely see more work on this. And particularly, I say particularly the data augmentation side. I think that's, at least to me, a little bit more interesting than the multitask learning approach. Just because I think that task, detecting single or multiple intents, like happening at every point in the dialogue, feels a little bit artificial, right? Because there's not necessarily any way for me to know, imagine like I'm an assistant, somebody says hi to me, and I have to predict whether they're going to like ask for two things or one thing. That feels very, it would be unintuitive to me if that ended up being really helpful for human assistant dialogues going forward. But I think that the data augmentation is definitely interesting. Right? We could all use more data.
Yeah, we could always use more data. We could always use unsupervised techniques to create more data, but again, yeah, it needs to be studied properly, and in my opinion, this one is not. And multiplied also by amount of mathematical notations that are absolutely not needed. So you can remove all the equations from this paper. This paper will become simpler and easier to understand, and no point it will lose any kind of any sense
It looks like the first author, this was part of their internship work, so I think they're gonna have a lot of time in their career to continue working on this and expanding on it. All right. Thank you for joining today, Boba.
Yeah, thank you for having me.
Yeah, it was nice. I enjoyed it. And tomorrow we're gonna have live coding, and I have to build a database so I can connect my assistant to it. So that's what I'm gonna be doing today. Yeah, I'll see y'all tomorrow morning, 9 a.m. Pacific, same time for live coding. Next Wednesday, we're going to be back with question answering, the office hours, and I don't have at my fingertips who's going to be joining me, but someone fantastic because the Rasa team is all great. And I'll see you there. So thanks so much for joining, Boba. Thanks for joining everybody on the stream, and we'll talk to you later.